Okay. Good morning, everybody, and welcome to the talk by Jacques Piennaar. It's a great pleasure to welcome him. Jacques received his PhD in 2013 from University of Queensland, in the group of Tim Ralph, working on gravitational decoherence and some nonlinear extension of quantum theory. And then he moved to Vienna, to ICOKI and University of Vienna, working in our group from 2013 to 2016. Also worked on quantum causal models, among other things. After that, he moved to Brazil, to Natal, to the group of Rafael Chavez as a postdoc from 2017 to 2019. And afterwards, he joined the Chris Fuchs group in Boston, University of Massachusetts, where he started to develop his own view on QBism, which is, I think, still one of the major focuses of your work. In the last 2 years, you are now in Rio de Janeiro Federal University as an independent researcher, and also running the John Templeton Foundation grant, which is related to quantum metrology and QBism. And if I may add, but it's just a personal remark, I find very enlightening his work on quantum Bayesianism, something which goes, it's a fresh look, and I think something which really is not dogmatically bounded. And that's why I think he has more freedom to investigate this and bring it forward. So today we have a talk about what is quantum, about quantum reference frames. I guess this is something maybe which is also interesting for us. And I think you point on some common feature that should be incorporated when you think about classical mixture of space-time as opposed to quantum superposition therefrom. Okay, thank you very much.
Thanks, Czeslaw. Oh, it's good to be back here. I haven't set foot in this institute since I left in 2016. I almost came for a visit. When was that? 2018, I think. But I had to call it off at the last minute. It didn't work out, and I was very sad because it would have been a wonderful opportunity to come back and see all these familiar faces. But yes, anyway, there will be lots of time afterwards. I'm free, most of today and tomorrow to have discussions with whoever wants to about anything you want. I have nothing on my agenda for most of this afternoon and tomorrow. So let me get into it so that I don't... oh, where's my talk now? There we go. Let me just go view show. So I'm committing a terrible sin today talking about research which is, first of all, it's research which I have not done yet. But second of all, it's research which has already been done by other people. But, it's just very interesting and exciting stuff. And I just want to convey to you what an interesting and exciting field this is at the moment. And maybe also give you a bit of my own unique perspective on this topic of quantum reference frames. And as you will see, my perspective is very much influenced by my work with Chris Fuchs on QBism. And I'll talk a little bit about that, how that has shaped my approach to this problem. Also because I know many people have heard of QBism but don't really know what it's about. So if anyone wants to talk to me more about that in depth afterwards, I'm happy to discuss. So this is just to give you a notion of my academic trajectory. I don't know if this pointer is on, is it? No, okay, never mind. I'll point with my finger, okay. See, I did my PhD over there in Australia, in Brisbane. And the theme, as Czeslaw said, was gravitational decoherence and nonlinear modifications of quantum mechanics, but there was already a focus on causality, and this field they call relativistic quantum information, which is kind of a generic term for any way of combining ideas from relativity with quantum information theory. So you can kind of see naturally how that led me to Vienna for my first postdoc, to Česlav's group, which is very much connected with these research themes. And it was here in Vienna that I really became interested in quantum foundations and interpretations of quantum theory, because, as many of you know, this is the hub of Vienna Copenhagenism, a sort of unique flavor of interpretation due mainly to Česlav and Anton Zeilinger. And it was the first time that I realized that maybe there's more to the Copenhagen interpretation than I had realized as an undergraduate. And I was particularly influenced by a talk that was given here by Carlo Rovelli on his relational interpretation of quantum mechanics. And that, I think, was the moment that really kicked off my fascination with foundations. But my way into it came through quantum causal networks, because I continued investigating this question of what is the meaning of causality in quantum mechanics. And actually, you're very lucky that there is someone else here who knows a lot about this topic, who is Romeu, my colleague from Brazil. So if you're interested in quantum causal networks, you can talk to me or to him. Or perhaps, I don't know if there are other people here who know about this, but it's very much... Sorry? I'm sorry, but yes. You know, it is a topic which unifies, not just Vienna is not only a hub of this, but of course we have some work on this in Brazil. So when I went to Natal, it was to work with Rafael Chaves, who worked on this stuff. And of course, Brisbane nowadays has Fabio. So in fact, it's grown into a huge area. But I kind of just rode the coattails of that because I did some early work, but then I kind of moved on to more foundations work. And it was through thinking about causality that led me to QBism eventually. And I ended up doing a postdoc with Chris Fuchs in 2019, and I was based at the University of Massachusetts, Boston for a while, and ultimately moved to Rio de Janeiro as part of this big Templeton grant, where I'm more and more interested in measurement, you see, because in Copenhagen interpretations in general, and QBism in particular, measurement is fundamental, but that means it's very important to understand, what is measurement. And there is this whole field which is all about measurement called metrology. So that's why I ended up in the quantum metrology group in Rio, where I am now. But this is all just background. Oh, what's that point there in South Africa? That's where I was born. So that just completes, I've been on all of the continents basically, except for Antarctica. But, maybe someday I'll go there too. Just to motivate a little bit this question of quantum reference frames and how did I come to be interested specifically in this? Well, in a way, the seeds have always been there in this question about causality and interpretations. Thinking about relativity, Einstein famously had these thought experiments where he imagined that he was riding along next to a light beam, which was, of course, impossible, but he liked to ask, well, what would you see in this situation? And similarly, people have sometimes wondered, what would you see if you were inside a superposition? Would you be able to tell? Would you feel different? These kinds of thought experiments, they can be informative, even if they're completely impractical. Wigner's friend is another good example of that one. But thinking about this idea of reference frames is very connected to these thought experiments. A reference frame is a hypothetical standpoint of observation. In other words, we imagine that we could put ourselves in that position and think about what things would look like from that place, even though it's actually impractical to, boost a spaceship to close to the speed of light. At least it's not forbidden by physical principles, and so that's enough for us to contemplate it. hypothetically. And I was always intrigued by that. And as we'll see, it's a little bit in tension with this idea of reference frames as physical things. But let me discuss a little bit some of the early work trying to think of this question, what is it like to be in a quantum superposition in a more rigorous way? So the earliest work on this that I know of was by Aronov and Kaufer. And in order to get a foothold on, to try to formalize what they meant by a quantum reference frame, they appealed to this very interesting principle, which they called an extension of Einstein's relativity principle, that it should not be possible by means of an experiment performed within one given reference frame to discover its state of motion. Therefore, the observer in the quantum reference frame may be in an eigenstate of position or momentum relative to some external frame, but it should be impossible for them to distinguish which one of those is the case. So the intuition here is that, think of Galileo's ship that's in constant uniform motion. You're doing experiments inside the ship. You cannot detect how fast it's moving relative to some external frame. And by the same token, these authors are suggesting that if the ship were in a quantum superposition of different uniform states of motion, you also should not be able to detect that you are in a quantum superposition, which I think is perfectly reasonable. In fact, there are various ways you can prove it using the formalism of quantum theory. But this was early days, and at that time, I think they lacked many of the mathematical tools needed to really make this idea precise. And so you can think of the whole timeline of research history on quantum reference frames as being a story of using more and more advanced mathematical techniques to try to formalize the consequences of this idea. And I think the major first turning point in this history was 2007, with the publication of an article by Bartlett, Rudolph, and Speckens, where they took a quantum information perspective. So they said, think about quantum reference frames in terms of information transmission. You can encode information instead of just thinking of encoding information in the internal degrees of freedom of a quantum system. You can encode it in the relative degrees of freedom between a qubit and some reference system. And so there's this kind of relational information. If you think, let's say, of the orientation of a spin qubit, that orientation is only defined relative to some classical external reference for orientation. And so there's, if you just send the qubit without sending the reference information, you will lose completely all of the information that's encoded in its orientation. So they studied using group theory all of the properties of quantum reference frames understood as physical systems with reference to which we are encoding information in some target system. And this perspective enabled them to employ all kinds of advanced techniques to discover many interesting things. One of the most important effects they discovered is there's a necessary back action on the reference system. Every time you use a quantum reference, meaning a physical system that is modeled as a quantum system, every time you use it as a reference for another system, let's say to tell what the orientation of your spin qubit is, when you do that measurement, there will be a certain back action on the reference system that will cause it to become a little bit less reliable as a reference. And over time, this can actually degrade its ability to be a good reference. Then, for a while, this generated a lot of interesting research. Another turning point, I think, came in 2019 with the work of Flaminia and Czaslaw. And Flaminia remains an important leader of this field. Also Esteban, who's here. And the idea here was that they kind of moved back a little bit towards that original intuition of what is it like to let's say to be in a quantum superposition, and the idea was to formally define transformations between different quantum reference frames. And so this was just kind of using a different perspective, and that turned out to be very useful because in 2024, it was realized that this can actually help you to make sense of what could be meant by a quantum superposition of spacetimes. And I'll explain a little bit why quantum reference frames are connected to superpositions of spacetime. But let me just summarize some of the key findings from this body of work that I will talk about today. This is by no means a complete list, just the ones that I picked to be interesting. The first point is this idea that quantum reference frames are physical, meaning that you really have to consider the physical modeling and the properties of your reference frame just in order to define what things look like from that frame. And another interesting feature, and this came mainly out of the work since 2019 with that Flaminius has pioneered, is this idea that quantum superposition and quantum entanglement is a frame-dependent notion. It can either be there or not, depending what reference frame you're in. The third point is this connection between reference frames and superpositions of spacetime, which connects to some very deep philosophical questions. And finally, this is a more technical point. There's something you can define called model dependence of a reference frame. And it has been claimed that quantum reference frames are distinguished from classical reference frames because they are model dependent. I'll explain what that means when we get to it. And the fifth point, which I think is where all this research is leading, is can we learn something about quantum gravity using the formalism of quantum reference frames? And this motivation, I think, is driving a lot of this research today, which partly is what makes it so exciting. But it's still very speculative. Now, QBism, how is that going to come into the story? Of course, it must come into the story somehow, because it's such an important part of my research history. Czaslaw suggested that I have my own flavor of QBism, which is non-dogmatic. It's true that, if the opposite of dogmatism is pragmatism, certainly I'm very much pragmatist. But I wouldn't say that I deviate from QBist principles in any way. I'm still very much in the same lineage of thinking as Chris Fuchs. I'm still very much promoter of the personalist Bayesian approach, and in fact, I think it's really central to QBism. If we lose that, it's something else, but it's not QBism. But I just want to stress that my research approach is to try and see, as any good pragmatist would do, what is the so-called cash value in thinking about things this way. Why would QBism be interesting at all? Only if it helps us to think in a certain way, which is useful for studying various research topics. And I want to suggest that my QBist perspective leads to a different, maybe more interesting way of thinking about quantum reference frames that would not have occurred to me otherwise. Now, you don't have to be a QBist to buy into what I say after this. I'm just telling you how I got there. But what I'm going to tell you definitely stems from this point of view. Now, the two main lessons of QBism that are relevant for us here are the following. The first tenet, if you like, is that quantum states are equivalent to probabilities. Now, this in itself is not very controversial within quantum information, because there we have this idea of an informationally complete measurement. If you fix a choice of information complete measurement, you can map every quantum state to a unique set of probabilities, which can then perfectly recover that quantum state, which allows you, in principle, to reformulate all of the quantum formalism in probabilistic language. And of course, this is very closely connected with reconstructions of quantum theory from generalized probabilistic theories. But the question is, well, why would we want to do that? And the motivation for QBism, at least, and this is historically true, although it's not the way it's often represented, the idea in the early days was that if we can reformulate quantum theory as a probabilistic theory, and particularly quantum states as sets of probabilities, then the problem of interpreting the quantum state reduces to the problem of interpreting probability. And fortunately, there is a lot of literature in philosophy of probability about that very question. And in fact, I think if you look at that literature, it's very difficult to escape from the idea that the best interpretation of probability is the Bayesian one. Now, among philosophers of probability, it's certainly a very popular choice. And it also turns out to be very useful for dissolving quantum paradoxes, as I'll explain on the next slide in brief. But the motivation for QBists was particularly to use this interpretation to make sense of the strange features of quantum theory. And in particular, they found that the subjective Bayesian flavor of Bayesianism, as opposed to the objective Bayesian, was more powerful for dissolving the quantum paradoxes. And that's why at the core of QBism, the idea, it's a two-step process. Quantum states are probabilities, and probabilities are subjective Bayesian. And there are two levels of personalism in the subjective Bayesian component. This follows the work of Ramsey and De Finetti. The first step is to say that the probabilities represent an agent's subjective degrees of belief about something that could happen to them. So the second degree of personalism is not just that the probabilities are subjective, but that the events that we're talking about are things that will happen to some given agent. So they're personal to the agent. Now, as I've said, you can take it or leave it, but it's coming from that mindset which leads me to this guiding principle. And there is some evidence in the literature that this is a fruitful way to think, that we should not attribute to quantum theory that which can be explained just by probability theory. And to give you some examples of what I mean, take the most obvious one is quantum state collapse. If you think of the quantum state as a physical property, then quantum state collapse is very surprising and shocking. But if you think of it just as a probability which I'm updating when I receive new information, there's no more mystery about it. At least the mystery changes. Another example is the no cloning theorem. Actually, no cloning of quantum states might seem surprising if you compare it to, say, deterministic classical physics. But if you think about probability distributions on a classical phase space, there is a complete analog of the no cloning theorem for Liouville distributions. Actually, this observation is what led to the discovery of the no broadcasting theorem, because really no broadcasting captures better the essence of quantum mechanics than the no cloning theorem. A third example is Spekin's toy theory. Now, just to be clear, Spekin's toy theory is not a strictly classical theory, because it has something called an epistemic restriction, which might seem a bit strange from the intuition of classical physics. But the point is that it's certainly not a quantum theory. It's maybe best called a local or non-contextual hidden variable theory with probability distributions that obey some restriction principles. And within that theory, you can qualitatively get many supposedly quantum effects. You can get entanglement as long as it's not violating any Bell inequality. You can get teleportation, incompatible measurements, interference, all kinds of things. And this shows that these effects really, at their root, qualitatively, They have their roots just in probability theory. They're not specifically quantum. So my conclusion from this is that it's useful to think about quantum physics in terms of probabilities, because then we can separate out what is really quantum from what is just classical probabilistic, or at least, let's say, generally probabilistic. And I would like to take that same attitude to quantum reference frames. So this is the list of things that I'll talk about, and I'm going to argue that each of the things on this list, quantum reference frames are physical, relativity of superposition and entanglement, and so on, they all have analogs just in what I'm going to call probabilistic reference frames. So I'm going to argue that we need to try to formalize the idea of a probabilistic reference frame that's not necessarily quantum, and this will help to illuminate what is really quantum about quantum reference frames. How long have I been talking? Is someone keeping track of time? Oh, good, okay. I think I'll be able to make it within an hour. So let's go. The first point is this one I mentioned earlier, that quantum reference frames are physical. What do I mean by that? Well, it's important to make a distinction between coordinate systems and reference frames. So every particular reference frame is, of course, naturally connected with some coordinate system, but the coordinate system is fundamentally an abstraction. You can talk about coordinate systems without ever explaining how you're going to implement them using apparatuses and so on. But the fact is that in physics, at the end of the day, in order to do experiments, we always need to physically instantiate a reference frame. The equivalent of, Einstein had some set of rigid rods and perfectly stable clocks. At the end of the day, we're going to need to use rods and clocks, and they won't be perfect either. So there's a kind of trivial sense in which reference frames in practice are always physical. We can only ever measure any quantity in reference to some other system. But there's also a more interesting question here, which is whether at the end of the day, in the theoretical analysis, we need to talk about the physical constitution of the reference system. And when you think of an example like relativity, the answer is that you don't. You can think of coordinate systems, but a coordinate system is completely abstracted away, exactly because it doesn't matter anymore how you realize your system of rods and clocks. As long as you are able to approximate a perfect reference, perfect rods, rigid rods, and stable clocks, to that degree, you can then plug in the coordinates. So in this sense, classically at least, you can abstract away the physical reference system, and you're just left with abstract coordinates. But it turns out that, yes. Well, if it's very short, I can. No, I think they're equally abstract. Yes. I want to highlight here that in the case of quantum reference systems, it's not so easy, in fact, maybe not even possible in principle, to abstract away the reference system. And that's really because of this back action effect that I mentioned earlier. Because your reference body is quantum mechanical, it's always going to matter, basically. There will, the classic example of Aronov and Kauffer was that if you want to measure the position of a particle very precisely, that means that your reference apparatus also has to be fairly well localized in position, but that means its momentum has to be very uncertain, and that means a short time later, its position will become much more uncertain. So if you want to do repeated measurements using the same position reference, it will very quickly become useless as a position reference. So it lacks stability in this sense, and this is one of the things we want from a reference system, unless it has extremely large mass. So you can specialize to some classical limit, but then of course, you're not really dealing with a quantum reference system anymore. So the really interesting case is where the quantum aspects of your reference system become important. That's the regime of interest here. That's when we say we're talking about a quantum reference system. Are you thinking of this work on... Yeah, that's right. Actually, my use of the term classical is perhaps... You could challenge me on that. It's you know, conventional in the literature to call this a classical limit, but actually maybe it's more like a limit of stability. I'm not entirely sure. I think what you're saying has to do with this well-known work on back action evading measurements, that there is in some sense you can achieve a, let's say, a classical-like stability within the subspace of a larger quantum system. Here in this talk, I really wanted to avoid using the label classical. It's a good point. But I guess maybe the lesson here is that generically in quantum mechanics, you cannot subtract away the reference apparatus. At least you need to do something very specific and careful if you want to achieve that. And in that sense, the physical modeling of your reference apparatus becomes much more important. So reference frames are physical in that sense. And I'd like to point out that there is also a sense in which probabilistic reference frames have to be physical. It's not quite the same sense, but let me see if I can make the argument to here. So this is an image I stole from Flaminius and et al.'s paper, Giacomini et al. Imagine that we are in some reference frame that I will call C, and there are two systems A and B. This is in the spatial representation, and A is in a superposition of two different locations, while and so is B, but while B is sort of spread out and peaked in some position. And the question is, can we say what the state of particle B is relative to the state of A? Now, this was dealt with in this article in terms of superpositions of position. But I want to argue that you could do the same thing with probabilities of position. These functions here could just be a 50-50 probability of finding particle A at these two positions. And in both cases, you can define the reference frame attached to the particle A just by considering the relative distances between A and B. So from A's point of view, the original reference frame now is delocalized there on the left. But you can see that, and now B is peaked at two different locations that correspond to the relative distance from your frame A. But if you're in frame A, by definition, your position is localized, because by being in frame A, we mean you take the position of particle A as the zero of your coordinate system. But here's an interesting consequence of this. The fact that we can do this, whether using quantum superpositions or, in fact, probability distributions, means that you have to consider A as some physical system in the following sense. Think about relativity. So for any moving body that's not acted on by a force, which we define as inertial motion, it must be possible to define some frame of reference in which that body appears to be stationary. This is just the relativity principle. Now, adding probabilities to the story should not change that fact. So if I have, let's say, different solutions to the dynamical equations that are inertial solutions. So in space-time, they'll just be different straight lines, different velocities. I could also take a probability distribution of those solutions, and that should give me a solution to the probabilistic equation, right? That should also qualify as an inertial state. And applying this principle, the relativity principle, there should be some reference frame in which that state is stationary. But you can see that if I just take a mixture of two different velocities, I can make one of them stationary or the other one by doing a coordinate transform, but I can never get the distribution to become peaked at just one velocity. If I restrict myself to translations, just to coordinate transformations. But if we think about this idea that I just described of taking a physical system, this particle A that could be here or there, as a reference system, you could imagine that this probability distribution of velocities of some system is perfectly correlated in the velocity degree of freedom with some other system. And if I am sure that these two systems are perfectly correlated in their velocity, I can use one of them as a reference frame for the other one. And from that point of view, the other one will become a delta distribution, and I can make it stationary. So the point is that we gain this benefit that we can, if we think about physical systems, even just probabilistic ones, as potential reference frames, it expands the scope of reference frame transformations that I can think about, such that I can maintain this relativity principle even in the probabilistic case. And I just note there in a footnote, it's interesting that the reason we can do this is because any probability distribution for some system A can always be extended to a larger probability distribution in which you have perfect correlations between A and some other system, and you obtain the original distribution as the marginal probability. This fact is no longer true for quantum states, so that will be important later. But I just want to highlight that this mathematical fact is what allows this to be possible in the probabilistic case. And a consequence of this is that the very same argument used in this article by Giacomini et al., that superpositions and entanglement are relative to the frame, can be used in exactly the same way to show that probabilistic mixing and just ordinary correlations, not necessarily entanglement, are relative to your frame. So once we allow that probabilistic physical systems can serve as reference frames for, let's say, position, then you can find examples like this one, where here we start with the case that I just described, where A and B are perfectly correlated, in this case, in their positions. And by jumping to the frame A, we see that B becomes localized in position relative to A. But notice that in this jump, initially, a system that we place at the origin of reference frame C can be not mixed. It can be a delta function. I know certainly where it is. After I do the jump, I'm no longer sure where C is. It's now in a mixture of two different possible locations. So we have that the system that was localized at C, whether it's in a mixed state or not, i.e. a probability distribution, is relative to what frame I'm in. And the same holds for correlations, because in the first frame, A and B are correlated in position, but once I do the jump, they're uncorrelated. So this is just to illustrate that by thinking about thinking in terms of probabilistic reference frames, these effects which seem like some strange quantum effect are actually generic for any probabilistic framework. Let me go now to the third point on the connection with superpositions of space-time. As you can guess, I'm going to swap out superpositions for probabilistic mixtures. How will that work? So what is the connection? Well, Schrödinger's lump is this famous thought experiment that illustrates why it's difficult to define a quantum superposition of spacetimes. We can very well imagine an experiment where we put a mass in a quantum superposition. You follow the usual Schrodinger's cat formula. You just have a very heavy cat that's maybe even has a significant gravitational field associated to it. And a mechanism that, depending on the decay of an atom, will put it in one location or another. And it's important to emphasize that in this thought experiment, we're just talking about a superposition of two different matter configurations. You know, the mass being close to these other material bodies or further away from these other material bodies. But none of this actually says anything about space-time. So what we want to get is to an expression like this, where we have a quantum state where there are space-times, two different space-times entering into the kets in the superposition. The difficulty is that I then need to map my matter distributions onto space-time points. And the question is, well, how do I do that? So, of course, you can always do it by picking a gauge, that is, by choosing some way of assigning coordinates, you know, to your material coincidences, right? To your observable quantities. But the whole point of general relativity is that if we want to, let's say we start by establishing that initially the mass is at point y and the origin is at point x, and we want to say that the origin stays in the same place, let's say x is equal to z, but the mass moves to a different point from where it was before, so point w is not equal to the point y, then we need to have a way of comparing the points in this manifold to the points in that manifold. But these two manifolds exist in different, let's say, alternative possible worlds. So how do we connect them? You know, we can pick some way of connecting them, but then we can do a diffeomorphism, just a coordinate transformation on one of them, and mess up the scheme. And so it seems that if we want to insist, which is something we do want to insist in general relativity, that coordinate transformations don't have any physical significance, it seems that we have no way of saying that we have a superposition of two different spacetimes, because that requires us to have a point-by-point identification between points in this manifold and points in that manifold. So basically, we need some way of fixing a gauge as being physically motivated in order to make sense of this superposition. And I want to point out, well, first let me just say that actually there is a physically motivated way of picking a gauge. And that's a topic of some work I'll talk about soon, collaboration between many people here at Vienna and some philosophers, including Jeremy Butterfield. But the argument is that you can think about different ways of breaking physical symmetry. They have, you know, you have law-like symmetry breaking and furniture-like symmetry breaking. So this table is furniture. It's not translationally invariant. It breaks translational invariant symmetry, but that's not a problem at the level of law-like symmetries. But the idea is, if you have some furniture that is you know, suitably, let's say, special or important, you can use that to give you a de facto reference frame, which you can then use to define things like superpositions of spacetimes, because that will fix a natural mapping of points between different manifolds. But the important point here is nothing about this argument is quantum. I could have said all of this without using those Dirac kets. I could have just used the elements in some probability distribution. The problem comes from the fact that we're comparing different possible worlds. But different possible worlds are already there when you consider probabilistic general relativity. So my point is that you already have this problem without needing to worry about Hilbert spaces. You can already try to solve this problem just at the level of probabilistic reference frames. It's a problem of probabilistic gravity, if you like, prior to quantum gravity. And here's a technical point related to this. So forgive me if this goes over some people's heads, but I think it's worth mentioning this. So I talked very heuristically about jumping into the reference frame of this particle A. Mathematically, how is that actually achieved? Well, effectively, it's by a controlled translation, because what you want to do in order to define the reference frame connected to particle A, which is initially at some uncertain location, what you want to do is transform things so that everything maintains the same relative position to particle A. So you want to preserve relative distances between physical bodies, but you want to do it in such a way that the particle A is always the zero of your coordinate system. And the natural way to do that is to just take the position of A as a control, which determines which translation to apply. So you apply a conditional translation to all of the systems conditioned on the location of A. And this is formally how they achieve this in the quantum case. And the very same trick works just for a classical probability distribution. I should stop saying classical. Anytime I say classical, I'm saying just for a probability distribution. It could be a generalized probability distribution. Don't want to bring classical baggage in there. But this control that you need to do in order to deal with probabilistic frames means that your frame transformation is model dependent. To understand the term, let me just go up a level of abstraction. And this is the article I mentioned before with Victoria Kabul and Chaslav and many others, where they come up with a general framework for thinking about reference frame transformations. The idea is that you have a diagram like this where every vertical line consists of many points that are related to each other by some symmetry transformation. In this case, we're talking about position, which the relevant symmetry is translations. So all the points on the same vertical line are states which are related by a translation, okay? When you have points on different lines, you cannot transform one into the other by doing translations. So that's the meaning of this diagram, okay? I use the word states. In the article, they call them models, just a terminology. But the point then is that we can define a reference frame as a way of choosing a unique representative from every vertical line. Technically, the vertical lines are fibers in a fiber bundle. And choosing a unique representative from each fiber gives you what they call a cross-section of that fiber. So these dotted lines here, these horizontal dotted lines, they cut across the lines at exactly one point. So each of these choices represents a different choice of reference frame in this very abstract language. You can think of it essentially as fixing a gauge relative to that symmetry. And the significant point here is that you can consider a very special case where all of your choices of frame are horizontal, which is what they call the model-independent case. And this corresponds to if your reference frame transformations applied the same transformation to all physical systems. So there's no control in this case. It's just a single unitary transformation, if you like. Or in the probabilistic case, just a deterministic transformation. But as I showed, if in the probabilistic case you're jumping into the frame of a particle whose position is not well localized, it's distributed according to some probability, you need to have a control. And in that case, just like in the quantum case, your reference frame will be defined by a non-horizontal line. And I'm highlighting this because in the article, reading the article, I had the impression that they were saying that there's something uniquely quantum about this model dependence. What I'm saying is that it's not uniquely quantum, it's a general feature of a probabilistic reference frame. And you can see that just by plugging in a mixed state into their formalism. So I should mention that I'm speaking heuristically here, but in principle, everything which I've said can be derived as a theorem using the formalism that exists by just restricting everything to a classical basis, making everything diagonal. I confess I haven't done that calculation, but I'm willing to bet that the results will confirm what I'm saying. So in the end, what is really quantum about quantum reference frames? Well, I mentioned this feature of broadcasting. It seems that in the quantum case, we cannot always find a quantum reference frame that will localize a system B in some quantity of interest. So if I have a system that's delocalized in position, and I want to jump into a frame such that its position is perfectly localized, or let's say its velocity, if you care about inertial motion, you can only do that if its delocalization is classical. Well, you're only guaranteed to be able to do it if it's just a classical mixture of those different positions. Because in that case, you know that you can find you can extend the distribution to a larger one that will recover the same marginal probabilities. In the quantum case, if you have a pure superposition of different positions, proof by contradiction, suppose there were some other system such that relative to the other system, your original system were in a precise position, then the two would have to be entangled as seen from the external frame. But that would imply that the reduced state of your original system would be maximally mixed, or at least mixed in that property of interest, contradicting your premise. So it seems that quantum mechanically, you're not always guaranteed to have a reference frame that makes perfectly definite your quantity of interest. And I suggest that this is really the interesting difference between the quantum and the classical case. And you can connect this to this idea of no broadcasting, because really what enables the classical frame to always do this is the fact that classical information, such as position information, can always be broadcast. Quantum mechanically, it cannot. That was just an illustration of what I said. So I'll skip that. And let me close in the last 5 minutes by saying some very speculative things about quantum gravity, because why not? So I've been trying to argue that if we think about quantum reference frames and quantum states in general, such as superpositions of spacetimes, as physical properties, we're going to miss what is really interesting here. So it's very important, I think, to think probabilistically, because that will allow us to separate out what is really quantum about, say, a quantum superposition of spacetimes. And perhaps there will be some puzzles that we could shed light on. So there's an interesting open question in the literature about whether these reference frame transformations have to be unitary maps. Because you could also consider a class of general, completely positive trace preserving maps, which will do much the same thing, that will allow you to, let's say, jump into the frame of that particle A. What's interesting about using such general transformations like that is that you might start out with a pure state and end up with a mixed state. Yes, I think, well, this I'm not sure about. In the article, they have a kind of complicated mathematical sense of inversion, but they're not reversible maps, from what I understood. I think what happens is they have some auxiliary information that if you supplement your map with that auxiliary information, then you can make it reversible. But it's kind of, yeah, I mean, it's something I want to understand better. It's, part of the motivation for thinking about these things. And I want to point out also that thinking probabilistically, I think, points to a very interesting, very basic foundational question in quantum gravity that has not been explored very much, which is that among, there are many proposals for why quantum gravity is hard. And I think it's generally appreciated that one of the problems is that classical general relativity is built upon the mathematics of smooth, perfectly continuous manifolds, and in quantum mechanics, things are very much discrete. But I think at the heart of this is really a tension between motion and measurement. Because one has to ask oneself, why is it so difficult to find something like the generalized probabilistic theory of gravity? Just classical gravity, make it probabilistic. Now, there have been some attempts, which I have not been able to understand. The most recent comprehensive attempt is by Lucian Hardy, which I have not been able to understand. If anyone can help me with that, I'd be grateful. But I think the point is that it's not something that's been very much investigated, and I think it needs to be. And I think what makes it difficult is that relativity, if you think of it as a principal theory, it's built up about statements about motion. Inertial motion is central. The equivalence principle, really an extension of the idea of inertial motion. So we need to understand what motion is in a situation where we can only talk about measurement outcomes. At least coming from my particular biased point of view, that's the question that we're faced with in quantum gravity. How do we define these concepts of motion without appealing to infinitely well-defined trajectories through space and time? What are the mathematical constructs we have to replace that with? So I will end there, leaving you with open questions. I have no answers for you today. Thank you.
Something like that. Okay, good. Thank you very much. I might just add something because you asked about the paper and whether we were strictly kind of committed to the quantum. I think you're absolutely right. We can change all the cats with some sharp classical distributions. We were aware of that, and there is a small paragraph which I was insisting very much to add, that what we mean with this superposition is also well-defined phases in front of that. But we leave for future work to find out how these phases can be extracted. But apart from this small, I think absolutely right. So please, I open the discussion. Yeah, Markus.
Yeah, thanks for a very nice talk. So there's one feature about quantum reference frames where I wonder whether you thought of having that probabilistically as well or not. So you could say that there is a difference between the actual or the counterfactual when you read a quantum reference frame. So I think you would guess when you go ahead and you really measure the quantum reference frame and read it physically, and now you do this to another frame and you want to translate from one to the other, it's kind of a channel, it's not unitary. But when you could say something like, oh, suppose I actually did measure A versus what I've obtained if I did measure B, then it could, for example, be unitary, right? So maybe this is one of the things that also points to the reason why there are so many different formalisms for quantum reference frames. Now, classically, probabilistically, I wonder if that happens too, or rather not. Perhaps not, because there's sort of a single basis in which you measure, everything commutes. So then maybe the actual and counterfactual, they are the same thing. Yeah, I wonder if you've thought of that aspect of this.
I'm not sure I understood specifically the technical details of what you're saying, but the gist of it sounds like, I mean, it's not something I specifically thought about, but I think it's a very natural thing to look at. I think that probabilistic changes of reference frame will also be irreversible, just because, when you, well, will they? Oh, now I'm not sure. Okay, no, let me I don't know. I think this is something important to look at, though. And also, I should mention that there's some interesting work, fairly recent work, by Eric Cavalcanti and a student of his on counterfactual reasoning in quantum theory, which may very well be relevant to that question. But yeah.
I have a question which I think it's very similar to yours. So I try with the different words, but you tell me, because that was my question actually, is that when we say that something is coordinate independent, like observables are coordinate independent in GR, there are two possible ways to understand what we mean with this. One is that we do use coordinates to measure observable, but then we see that no matter which coordinate we use, we get the same result. And the other, which is actual, the other is you don't use any coordinates too. You don't need to, I don't know how you measure it, but you don't need to use this. Is it along these lines? Okay, I think that's exactly the same question then. I don't know whether you want to comment now on that or.
I think we need to leave this for afterwards. I haven't thought, enough to say I haven't thought about this in sufficient depth.
Yeah. Okay, are there further questions? Yeah, wait a minute, because it's recorded.
Okay, thanks for the great talk. It was really interesting. So I have one comment and two pretty random technical questions if you want to answer them. So a comment is that in the operational approach that I work on, that you mentioned of Loveridge and Carrette, I think, yeah, in some sense it does lie in between quantum and probabilistic approach to thinking about these problems. And I think it does have a clearly defined sub-theory that you could maybe look at as the probabilistic framework for frames, very concretely. And there's also a place in there to think about informationally complete quantum, in this case, frames, so maybe that's also interesting. And the frame transformations that we get in this setup are indeed non-unitary, but can be made invertible. So I'm happy to talk about these things tomorrow, maybe, if you have time.
Yeah, I'd be very interested to talk with you about that.
And then, yeah, just two questions. So this existence of informationally complete POVMs, I just don't know how general it is, so maybe you know, like, is there always a unique one, or like, does it depend on some group symmetry structures as well? This sort of things. And also, what are your thoughts about, because you really want to, in this, as far as I understand, in this QBism way of thinking about these things, you want to really equate the resulting probability distribution with the quantum state. But to do this, you need this link, this informationally complete POVM. So in a sense, the need for the quantum formalism somehow remains, but you're able to, so yeah, this uniqueness questions, this sort of things. And then the last one is about QBism and the stochastics approaches to quantum, so trying to understand quantum mechanics, especially the recent one by Barandas. If you have any thoughts on this. Okay, thanks.
You know, I'm wondering, maybe maybe I can answer you by asking you a question. So the role in this formalism that you work on, the informationally complete measurement, I take it, it's important because exactly for the reasons that Miguel and Marcos raised, which is this question of counterfactual measurements. So in QBism, we use it because if you have a measurement which you do not perform, nevertheless, it's meaningful to say what the probabilities would be that you would assign to that measurement. And if it's informationally complete, you can use that set of probabilities to figure out what you should assign for any measurement that you do perform. So you use the counterfactual probability assignments to determine the probabilities for an actual measurement. And in this sense, those probabilities serve as an ultimate reference from which you can derive particular, let's say, perspectives. And I wonder if what you're doing in the formalism is something like that. In order to kind of, you know, Miguel said, like, are these transformations irreversible? I guess in some sense they must be, but I imagine it maybe if you have something like an informationally complete measurement specified in the background, that will always contain sufficient information for you to recover, what would have been the result of some other measurement. Is that more or less how you're using them?
The answer is no, so that's not what we do. So in this approach, the quantum reference frame is defined with a POVM that has some properties, and having it be informationally complete is a special case that we haven't really studied.
Okay, so you don't require them to be information.
No,
Okay,
no,
interesting. Well, the good news is that it's, in a given Hilbert space, infinite and I think also infinite, although I'm not really sure how it works in the infinite dimensional case, but you can always find some information complete POVM. In fact, there'll be an infinite class of them. But the question is really whether it obeys certain symmetries. The famous case is the symmetric information complete POVM, which are not, it's not proven whether they exist in all dimensions because they have a very strong symmetry requirement. But if you're willing to drop that requirement, you can always find something that will function.
Sure, but then your identification of states and quantum states and probability distributions is subject to this choice.
Yes, exactly. The precise mapping will depend on your choice of reference.
Do you see how this choice fits into the quantum Bayesianism way of thinking?
Honestly, I tend to think of it more like a choice of coordinates, more in analogy with relativity theory. That, yes, it will affect the mathematical representation of the quantities, but it doesn't have a physical significance. If it turned out that symmetric information complete measurements did not exist in all dimensions, you could still save QBism by choosing some other ICP-OVM. But it wouldn't be as nice.
Yes, thanks a lot.
Are there any further questions? And abuse my role for one last. And it is, okay, as long as you think about like commutative groups, or maybe just like one of the set of commuting observables, let's say just position, then I see this immediate kind of relevance of that if you ignore anything which will involve measuring of the phases in the case of translations, then really it's just a classical reference or probabilistic reference frames. Now the interesting thing comes when you involve also non-commuting observable and momentum, of course. Now still okay, and then you have to involve other groups, maybe Galilean group, okay? Then you have some kind of something which should, okay, still there is a room for extension of the probabilistic framework towards, I would say, toy model of Rob Speckens. Like you want somehow to mimic as much as you can, and maybe you can deal with some measurements, like specific measurements, of course, maybe just position momentum. So one could combine toy model with probabilistic reference frame. And then there is the last point in proving that it's not like. do you see this, or are you interested in extending this? Or?
Yes, I mentioned the toy model because part of what motivated me was a desire for something a little bit like a Speckens toy model for quantum reference frames, where you could have something that was based on some loose physical definition of what you mean by classical, maybe commuting observables, or no, you need something more general than that. Let's say non-contextuality. I don't know how you would formulate that with reference frames, but some way of doing it that you could say, well, here are some effects which are already at least qualitatively present without quantum mechanics. And therefore, it makes you look for the difference somewhere else, maybe look for a violation of some statistical inequalities or something like that. I think that would be extremely useful to have a framework like that. I'm not sure to what extent one can achieve this just by taking a, let's say, information theoretic classical limit of the existing frameworks. I think, this operational formulation might be particularly useful for that because it's inherently more, it's all about density operators and CPT maps. But there is an interesting, I can't resist mentioning a conceptual point. At the beginning of my talk, I explained why you need to have even a probabilistic, say, classical reference frame has to be physical, because you cannot, if you have a distribution, say, of two different velocities, you cannot make it stationary. But actually, that doesn't matter if it's a hidden variable interpretation. Like the Speckins toy model, you're always imagining that underneath there's some true state of affairs, and you just are ignorant of what it is. But if we do that, in the present case, this example I gave doesn't matter, because you can say, well, actually, one of these two possible velocities is the correct one, and the other one is wrong. So in fact, there is a coordinate transformation that will do the trick. You just don't know which one it is, but it's one of them. So there's no need to introduce a new concept of reference frame. You don't need to define a formalism for jumping into a probabilistic frame if you believe in the hidden variable underneath. So somehow, in order to make the, let's say, probabilistic reference frames interesting, you have to forget about hidden variables. It has to be inherently probabilistic in some way.
Good, thank you very much. And with this we conclude.